Have started. मेरी screen visible है and am I audible?
Yes, sir. Yes, sir.
Okay. So today we are going to discuss about multiplexing strategies. Uh, these are the brief outline of what we will be discussing. So you're already aware of what time division multiplexing is. The same strategy is also employed in optical fiber communication, and in this it is known as optical time division multiplexing. Okay. So here, of course, with conventional electronic time division multiplexing, you do not get very high data rates. In case of this optical or time division multiplexing, or OTDM in short, it's possible to get data rates of the order of 40 Gbps also. So So if you have a 10 Gbps signal in the electronic version, you can combine four such electronic TDM signals and get a 40 Gbps signal. So this is what is referred to as a four-channel OTDM system. Okay, so these systems would need very advanced semiconductor lasers, and these are known as mode locked lasers. And mode locking is a technique to get a single frequency out of a uh, laser cavity. Usually, it's possible that you may have three or four uh, modes which can come out of a laser cavity. But if you do the mode locking, then it's you can assure that a single mode would come out of the laser cavity. So mode locking is an very critical technique to have uh, very narrow line widths, and uh, these can also produce very short optical pulses. And with very short optical pulses, you can club more data onto the link. Uh, this is a block diagram of how OTDM can be used. You have, if you have multi Gbps, sorry, so what the block here shows is that you have a clock and there is a delay introduced, and when you have four different transmitters and each transmitter is working at 40 Gbps, then all these four can be clubbed together onto a single fiber by using a OTDM multiplexer, and the fiber can transmit it to a certain distance of maybe around 50 to 100 kilometers, and you can have a demultiplexing, and there would also be necessity of timing recovery, uh, and then you can have your uh, respective 40 Gbps signals back. So another multiplexing strategy is subcarrier multiplexing. I think we have discussed about this word, subcarrier multiplexing, in which multiple carriers or multiple electrical carriers are used to generate signals, and these multiple electrical carriers are uh, all multiplexed into a single optical carrier. So within a single optical carrier, you have multiple electrical carriers. So that is the reason these are known as subcarriers, electrical subcarriers. Okay. Uh, these can be of different frequencies. So it can be microwave or RF, and these can all be transmitted over single mode fibers. And this is attractive for video distribution systems. Okay. So uh, this is a block diagram of how this video transmission is carried out using subcarrier multiplexing over fibers. So you have a digital or analog video which uses single baseband electrical RF or microwave frequency, and all these multiple frequencies are combined together and transmitted over a fiber. And after conversion into back into the electrical domain, uh, all the different frequencies need to be filtered out separately, and then a voltage controlled oscillator can transmit or can relay the received digital or analog video um, to the necessary users. There are some limitations of this subcarrier multiplexing. This looks very simple, but there are advantages because of, there are disadvantages because of the Non-linearity is present in the source and also along the channel. So there are distortions also which are introduced into the system, and because of this, subcarrier multiplexing requires more bandwidth per channel than a TDM system. So what this refers to is electrical TDM. Another multiplexing strategy is optical orthogonal frequency division multiplexing. And have you heard of this orthogonal frequency division multiplexing? ये पढ़ाई हो रहा है या नहीं हो रहा है? डिजिटल कम्युनिकेशन में पढ़ चुके हो या नहीं? Is anyone listening?
Yes.
So, have you studied about this orthogonal frequency division multiplexing? डिजिटल कम्युनिकेशन में पढ़े हो या नहीं?
Is it similar to quadrature?
No, this is different. Okay, so anyway, I believe you're already familiar with frequency division multiplexing. So the top part shows this FDM or frequency division multiplexing, and here you can see that multiple frequencies are all transmitted uh, with a guard band in between, so that there is no overlapping of the information contained in one frequency with another. Okay, so this is how frequency division multiplexing works. In case of orthogonal frequency division multiplexing, what happens is the frequencies are uh, much more squeezed together. The multiple subcarriers are overlapping with each other. Okay, and here you should keep in mind that you should notice this particular feature, that at the peak of the first subcarrier, the second subcarrier has a zero. Okay, the second subcarrier has a zero. So this is possible to implement because present day whatever filtering technologies that are available, those are able to mm, filter out very narrow frequencies. So because of that, if only a single frequency is sampled out of this entire band, then you can recover the information which was transmitted uh, at each of these uh, subcarriers. Okay, so if you sample only this particular peak, then the other the information contained from the neighboring subcarrier that has a zero at this particular peak, so there will not be any interference. If you look at the second peak, the first and third are overlapping, but at the peak both have a zero. Okay, so that is the reason by sampling just the peak frequencies, people are able to demultiplex the required information. So by this method, you get a lot of saving in the bandwidth. So this is orthogonal frequency division multiplexing. So this is also the concept is similar in terms of getting these OFDM signals onto the optical fiber. You need to convert this entire electrical signal onto the optical signals by using a laser. So this is about optical orthogonal frequency division multiplexing. So here the multiplexing approach is similar to the subcarrier multiplexing. Next is wavelength division multiplexing. I think we have already discussed about wavelength division multiplexing. So what wavelength division multiplexing does is you have a single laser wavelength, and that has a line width of maybe something around 1 to 2 nanometers. Okay, so and the optical fiber, uh, as we have studied in previous classes, has very has a very wide wavelength range over which data can be transmitted or optical signals can be transmitted. The conventional band is around the 1550 nanometers, and there is the long the the long communications band, which is around the 1600 nanometer window. So uh, these multiple windows, this is spread around something around 400 nanometers. So it starts from something around 1300 nanometers and it goes up to 1700 nanometers. So in all these 400 nanometers of wide wavelength range which is available, if a laser uses only 1 or 2 nanometers, then it's always possible that you can club multiple wavelengths onto the same optical fiber. So that is the concept of wavelength division multiplexing, wherein you transmit multiple wavelengths on the single optical fiber. So this is analogous to frequency division multiplexing in the electrical domain. But what is different here is each of the wavelength, optical wavelength which you are transmitting inside a WDM signal can have an FDM signal, mm, or it can also have a subcarrier multiplexed signal or an orthogonal OFDM, orthogonal frequency division multiplex signal. So each wavelength can have different electrical data. So WDM is a larger capacity which it can offer. Okay, so the number of wavelengths, if you assume that a laser is transmitting 2 nanometers and you use a guard band of something like say 2 nanometers, then each channel would need about 4 nanometers. So you can transmit 100 wavelengths over the 400 nanometers of the wavelength range which is available for transmission. So if each wavelength can transmit about 10 Gbps, you can expect 1 Tbps of uh, data transmission with 100 channels of uh, WDM. So that is the range of the capacity that WDM offers. So there are different ways of having your data transmission. The first, the top block shows simplex data transmission, in which a transmitter is transmitting and there's a receiver which is receiving. So it's a single wavelength and it's unidirectional communication from the transmitter to the source. So apart from simplex, you can also have duplex transmission, which means you're having two-way communication. So you have uh, from the left end, the transmitter is transmitting wavelength lambda 1, and this is transmitting this onto the fiber. Okay, and at the receiver end, this is going to the receiver, the wavelength lambda 1 is going to the receiver, and uh, the right this transmitter is transmitting a wavelength lambda 2, which is being carried by the same fiber, and uh, this is being received at the left end. Okay, so you need a duplexer to do this wavelength routing operation. So if whatever wavelength which comes in from this transmitter, that has to go onto the fiber, and whatever wavelength which is coming back from the fiber, that has to be routed towards the receiver. So that is the function of the duplexer. I think I had mentioned about what is that? A circulator, right? So an optical circulator can also uh, do this desired function of a duplexer. And going ahead, uh, if you're transmitting multiple wavelengths, you can uh, club all of these wavelengths by using a multiplexer onto the single fiber, and all these wavelengths can be demultiplexed and transmitted to different receivers. So this is what is the basic concept of wavelength division multiplexing. So in wavelength division multiplexing, WDM by itself is now categorized under coarse WDM, wherein the guard band is much higher. Okay, and there is a dense WDM, in which case the guard band is much less. And along with the guard band, even the line width of the source which is used, that is also smaller. So, uh, as the name suggests, there are more wavelengths which can be uh, uh, which can be transmitted over a single fiber in case of dense WDM. So if you have about 100 wavelengths which you can transmit over WDM, then in dense WDM you'll be transmitting maybe around 400, something around 400 wavelengths which you can transmit over a single fiber. So this is wider channel spacing, and the channel spacing in case of dense WDM is much less. So this is about basic concept is similar. So what you can see here, you have multiple wavelengths and you have a multiplexer which will club all these wavelengths onto a fiber. An EDFA is commonly used whenever you need long distance communication, and so this is helpful for amplification of the signals. And after transmission of a certain distance of maybe around 100 kilometers, there would, because of the loss along the channel, you'll need some more amplification, and in between uh, dispersion compensating fiber, or some length of the dispersion compensating fiber is introduced, so that you do not have pulse overlapping along the fiber link. And then after that, further amplification is done and transmitted over further distance. So by this you can achieve distances of the order of means by using multiple EDFAs and these dispersion compensating elements, and sections. So if you can introduce many sections like this type of a system can be transmitted over distances of thousands of kilometers, and this is what is commonly used for undersea communications. Yeah, in limitations, what is mentioned here is just additional losses, but because of uh, a large number of wavelengths which are transmitted over the fiber, the optical power uh, can cause nonlinear effects to be displayed along the fiber. So it's possible that at some moment of time, the power which is being transmitted on lambda 1, some of the power from lambda 1 would be transferred to lambda 2, or maybe lambda 3, or maybe lambda n. You do not know, because there are multiple non-linearities which can occur in an optical fiber. I think I had mentioned about these non-linearities, like four wave mixing and self phase modulation and cross phase modulation. So all these nonlinear effects can introduce different types of losses along the communication link. Another last multiplexing technology that is being studied is optical code division multiplexing. Uh, Presently, I have not come across any implementation of optical code division multiplexing. But yeah, this is a very interesting technique by which you can transmit multiple information sources, uh, and this by this method, of course, the bandwidth that you need is higher, but with the higher bandwidth, the reliability of recovering the signals is also higher. Uh, so in this you can have codes, uh, and each transmitter would use a specific code send the signals, and the receiver would identify which transmitter is sending the information by decoding each of the codes. So this is similar to the spread spectrum transmission, which is commonly used, which is not presently being used in wireless transmission, but it was used widely uh, in wireless transmission few years back also. So this is a basic block diagram of how the code division multiplexing works. You have three different uh, transmitters, and all the three transmitters use different encoders. So you can see at the output of the encoder, the pulse pattern that you have at the output of encoder A and encoder B and encoder C, this is different. So even if all of these is combined onto a single fiber, okay, the decoder would be able to identify a particular uh, transmitter. So if there is a receiver which wants to uh, only receive from A, only receive from what was transmitted from A, then this decoder would be tuned to uh, this encoder A, and accordingly the output which it would get directly from A. So what is shown here is a variable decoder. So if you can implement so if one can implement a variable decoder, then all of the data can be uh, separated out, or it's also possible that you split this signal into different parts and use different decoders to get the transmitted information back. So this is about optical code division multiplexing. So there are many coding schemes which people have proposed, and there are people who are still working on this code division multiplexing, which can enhance the reliability of the system. But it may take maybe some time before this technology is actually used, because there are also limitations the in this multiplexing strategy, because it is not bandwidth efficient. It consumes a lot of bandwidth. So with the same bandwidth as what is necessary for optical code division multiplexing, you can transmit 10 times the data by using the optical time division multiplexing technique. So this is the drawback of this technique, and hence it's not implemented and used right now. But it is an option which is available where bandwidth is not a very hard and fast strict limit. Now, hybrid multiplexing is a possibility. You can use wavelength division multiplexing along with time division multiplexing, or you can use wavelength division multiplexing with code division multiplexing. Uh, so these combinations of the different multiplexing strategies is what is known as hybrid multiplexing. So most common hybrid multiplexing is the WDM OTDM, because it is the least bandwidth consuming system. Okay, so this is about the multiplexing strategies which are possible in optical fiber communications. So anyone having any queries? Any queries? If you do not have anything to ask, you all can leave.